In this particular problem, we're trying to calculate the pressure at the bottom of a tank that contains a fluid. This is a sealed tank, and we have a pressure above the fluid equal to 1.5 atmospheres. We're given the volume being 15,000 liters of liquid with a specific gravity of 1.35, and we find that the tank diameter is 2 meters, and we need to calculate the pressure at the bottom of the tank in units of atmospheres. Well, the pressure at the bottom of the tank will equal the pressure of the tank above the liquid level plus the pressure exerted by the fluid, which is given to us as rho GH. We're going to need to calculate the density of this fluid, and we know that specific gravity times our reference density will give us the density of our fluid. So that will equal 1.35 times the density of our reference fluid, being water. And units of kilograms per cubic meter are preferable in this problem, so we'll use 1,000 kilograms per cubic meter of water, giving us a solution density of 1,350 kilograms per cubic meter. The height of the fluid in the tank is just the volume of that fluid divided by the cross-sectional area. The volume is 15,000 liters, but to get it in units of dimensions of length, we have to use a conversion factor, knowing that a cubic meter is equal to 1,000 liters. Therefore, our volume is 15 cubic meters. The cross-sectional area is just the pi times the diameter squared over 4. In our problem, our diameter is 2 meters, so we'll have pi 2 squared meters squared over 4, or 3.14 square meters. The height will be the volume divided by that area, and the liquid level will be 4.77 meters. Calculating the bottom pressure, we find it convenient to use units of pascals. So we'll convert the pressure above the fluid from 1.5 atmospheres into pascals, and then we'll add the fluid pressure, which is just rho GH, and then converting our units of measurement into pascals from there. Plugging in our numbers, we determine that the pressure at the bottom of the tank is 215,156 pascals. We then can convert that back to atmospheres, and the solution of our problem will find that the pressure is 2.12 atmospheres. In problem 2, we are accelerating a 20 metric ton object at an acceleration of 50 feet per second squared, and we want to determine what the force is in pounds force needed to achieve this acceleration. We know our formula for force is equal to mass times acceleration. Therefore, we put in our 20 metric tons. We'll convert this to kilograms, knowing that there's 1,000 kilograms for every metric ton. Our mass conversion into pound mass is 2.205 pounds per kilogram. Acceleration is 50 feet per second squared. And now we need to convert this into units of pound force. Recognize that a pound force is the force delivered when a 32.174 pound mass object is accelerated at 1 foot per second squared. Therefore, the solution is 68,534 pound force. Problem 3, we have 100 gallons per minute of a liquid flowing into a tank for 2 hours. And we want to know what the weight of the fluid in the tank would be in units of newtons. Well, weight is just the mass times acceleration of gravity. And the density of our fluid is its specific gravity times the reference density. So that will be 0.8. And a convenient unit in this particular problem for the density of water would be 1 kilogram per liter. So our fluid has a density of 0.8 kilograms per liter. The weight will be the 100 gallons per minute flowing for a period of 2 hours. We will need to also convert 60 minutes into an hour using a conversion factor that there's 3.785 liters per gallon. We can then multiply it by the density of 0.8 kilograms per liter times acceleration of gravity of 9.8 meters per second squared, and then convert that knowing that 1 Newton is equal to 1 kilogram meter per second squared. And so the weight of this liquid would be 356,093 newtons. We have a mixture of sodium hydroxide and water flowing through a pipe, and the flow rate is 25 cubic feet per hour, and we're given the specific gravity of 1.25. And knowing that the mass fraction of sodium hydroxide in the mixture is 0.3, we're to determine what the mass flow rate of just the sodium hydroxide in units of pound mass per minute. Our density of our mixture is just the specific gravity times the reference density. Our specific gravity is 1.25, and the reference density of water, a convenient unit for this problem, would be 62.43 pound mass per cubic foot. This will give us a density of the mixture of 78.04 pound mass per cubic foot. Mass flow rate of sodium hydroxide. We'll first determine the mass flow rate of the mixture, which will be its volumetric flow rate in cubic feet per hour, and we'll multiply it by its density, and then convert hours into minutes. And then we know that there's 0.3 pounds of sodium hydroxide for every pound of mixture. And doing the calculation will determine that we will have 9.75 pound mass of sodium hydroxide flowing for every minute. In this problem, we're given a composition of a gas on a mole basis, which contains hydrogen, carbon dioxide, and carbon monoxide. And we're asked to calculate the mass fraction of each component for this mixture. So we first want to take a basis of this gas, and I chose 100 moles of this mixture. The mass of hydrogen in this mixture would be the total number of moles times the mole fraction of hydrogen, in this case 0.3, and we need to know the molecular weight of hydrogen, and that's given to us as 2 grams per mole. So for 100 moles of mixture, I would calculate to have 60 grams of hydrogen. We'll do the same thing for carbon dioxide using its mole fraction and its molecular weight to determine to have 2,640 grams of carbon dioxide. And by similar calculation, we'll have 280 grams of carbon monoxide. This gives us a total mass for 100 moles of mixture to be 2,980 grams. Note that the mass fraction is just the mass of a component divided by the total mass. And so we can use this formula to determine the mass fractions of all 3 components given below. So for our hydrogen, it is approximately a mass fraction of 0.02, carbon dioxide, and mass fraction of 0.886, and for carbon monoxide, the mass fraction will equal 0.094. In this problem, we're trying to determine how much lithium would be necessary to add to a lake such that we would end up with a concentration of 250 parts per million. We're given that the lake has a volume of 50 cubic kilometers, and we are to assume that there is no lithium present in the lake before we add any. Well, the mass of the lake is given to us by the density of the lake times the volume, and we'll use the density of that being pure water, or 1,000 kilograms per cubic meter. Now the volume is given to us in cubic kilometers, and so we also have to convert cubic meters into kilometers using the equation given there. And so the total mass of water in this lake is 50 times 10 to the 12th kilograms. the mass of lithium will be equal to its mass fraction, which is given to us in parts per million, meaning that we would have 250 kilograms of lithium for every million kilograms of lake water. And then we would multiply it by the mass of the lake that we just calculated above. And since the mass units will be quite large, I converted that mass into tons and determined that to get 250 parts per million of lithium in this lake, we would require 12.5 million tons of lithium to accomplish this.